Today I want to talk to you about some experiments we've been doing at the Atlanta Zoo. Every Friday for the last year and a half. My postdoc, Jianing Wu, he's shown this in this slide, has been going to the Atlanta Zoo with various implements to answer the question, how elephants are so versatile with their trunk. How can they grab both a peanut and a log? And this is a length scale difference of a weight scale difference of between 10 grams. We don't use peanuts. They have a peanut allergy. I'm just kidding. But these are tortilla chips, which the elephants seem to like. These are granular materials. These are crushed up cereal flakes. These are potato wedges. You call them crisps here? No, chips. Chips. And this is a 135 kilogram weightlifting apparatus. So I'll show a little bit about how the elephant deals with each of these situations today. And this work it's funded by the Army Research Office, who's interested in basically general principles for elastic systems across this large scale of weights. So I'm ashamed to say I have only n equals 2. It turns out with elephants, they live 30 to 70 years. They require 8 people to train. They require 2 people during the experiments to make sure that we're not killed during the experiments. So all the experiments are shown with a 35-year-old elephant, Kelly, whose favorite toy is a hanging log. The other data point is there was an elephant who died at the National Zoo in 2009. And her trunk has been preserved in the freezer there for about the last 10 years. And we had the pleasure to dissect it a few months ago. It kind of looks like dry-aged steak. And I'll show you some images and things of that. So the elephant tongue is interesting that it actually takes practice using it. The juvenile elephants actually are not very dexterous with their tongue. They basically take a long time to pick things up and learn how to use it. And as Alan Gorelli was telling me, they also have one of the largest cerebellums. And some people think that's due to their actually having to be able to figure out how to use this trunk over their lifetime. But when they do use it, they're surprisingly versatile. This is an example of, I guess, stupid American tourist. You'd probably see that a lot here. But I mean, they can move their trunks very, very quickly. This is an example of someone actually got knocked down by a trunk. So that wasn't. It's basically they can move their trunks at 3 times acceleration of gravity if they want. And sometimes the videos I'll show will in fact involve high-speed video because we actually can't see what they do unless we see it at high speed. So I'm going to show you a series of videos where we give them different food items. We try to keep the weight the same, but relatively the same, but changing the size. And that will affect basically how much forces they have to use to collect these things. And I'm going to turn the sound on for this one. So they're very creative in how they grab these things. You have to keep in mind these trunks are 100 kilograms. They're eating pretty much 80% of the time they're awake, which is almost 20 hours a day. So they really want to basically spend as few trips as possible to grab the food. I think the energetic use of actually extending the trunk is small, but the time they would lose if they would grab each piece would be substantial. This basically wrapping technique is made possible by the inside of the trunk is actually slightly concave. And basically the entire thing is coated with hairs that allow it to have high friction. But you can imagine this still takes a great deal of practice to be able to grab all these things with only leaving a few on the bottom. So once they grab it in this fashion, they'll actually projectile throw it into the mouth. They won't actually expend the time to actually put it in their mouth. They'll just throw it in. All right, so I want to basically show a regime diagram of the 2 basically new ways we found that elephants have grabbed small particles. This one, it's important to have sound. And so maybe you might hear something that is familiar to you if you go to Chinese restaurants. I'll play it again. So that's the sound of slurping noodles. But it doesn't always happen. Basically, it depends on the number of items you give them and the distribution. Like, for example, this one, they just gather them without much slurping. Okay. So there's this is basically the number of items that we've provided and the size of the food item. Suction seems to appear basically when there's large numbers of sort of small items. When it gets down to a powder form, they're smart enough to not use suction because that will actually just bring it into their lungs. But there's this regime here where basically if they're close enough and there's enough items, they'll really use suction to help them grab onto it. And I'll provide a model for basically how far away you have to be from these items to be able to grab onto this. When the items are too large, for example, when you give them big chunks of potato, they won't bother using suction. They'll simply use the prehensile tip to basically grab these things. But somehow when they see these things or when they feel them, they get an idea that suction is basically useful for this regime. So to test basically their limits of how much they could suck, we gave them tortilla chips. It's actually an entire tortilla, which is about 10 grams. And this is a high-speed video of them grabbing it. So their vision is not very good. And they're not intoxicated either. This is just what they do. So they sort of find the force plate, and that's sort of a large contact force. Then they sort of rummage around with basically applying very little forces, and they kind of finally find it, and they just basically move closer to the top. And then once they stick to the top, they seem to apply this magical force that helps it stick to the tip. And it's important that they're not constrained. Their trunk is not constrained. If basically we hide their vision, they easily break it. In fact, they're almost breaking this entire container to grab this chip. Here's another video. So there's basically two techniques. One which they'll apply their trunk directly to the top. Another one which they'll hold their trunk a little bit above the chip and suck it upward. I think this is the same video as I showed before. But this is an example of where they'll basically go slightly upward, and we'll see the chip just rise when it's right underneath. So the way that it holds on is simply by the pressure force due to basically them pulling air into the trunk. So the chip weighs about 10 grams, and so we basically consider the area of the chip. It's about this large, and our goal is to figure out what the pressure is required to be able to make this thing rise. Okay, and we basically have an unknown parameter, which is the pressure they apply from the lungs. But we basically use a technique involving water suction to be able to measure that pressure. But if we know the pressure applied from the lungs and we know the roughness of the wall, we can basically get an estimate of how the flow velocity changes as we go towards the tip. Then the whole problem with sucking, and the reason why it's so difficult, is because as you go further and further away from the tip, conservation of mass tells you that you basically have less and less flow. Imagine you have either a spherical shell or a hemisphere that basically the flow velocity decreases with the surface area around. The nasal passage, they're quite large, so their nostrils are about 3 centimeters in diameter, like this wide, and that's actually plays a big role in them sucking these things up. But the final formula where we basically use this Bernoulli equation is concentration mass. We can write the radius that they're separated from this chip as a function of basically the velocity they're sucking, the area, the radius of the nostril, the area of the chip, and the mass of the chip. So how do we actually figure out the pressure force? The easiest way to do that is with water, and that's something they do very well. So that was 3 liters of water in about a single second. So it actually takes a long time to do these experiments because these tanks are really filled with water. All right. And this is sort of the largest a bubble tea made. This is, we made chia seeds, soaked them in water, so we could use them as flow visualizers. Basically, everything we give the elephants has to be edible. And this is sort of an underside view of basically of what happens. In National Geographic, they had this hypothesis that the trunk of the elephant is extensible. In fact, no one actually knows why the nostrils have radiating muscles coming out of it. And I'll show you some images as we do a dissection of that. And in fact, if you measure the volume that was sucked up in water, it's something like 6 liters. But given the height of the trunk and the diameter of the nostrils, you only get basically half that volume. So it probably is necessary that they expand inside their nostrils, but we can't really see it in this view. So they suck at about 3 liters per second. That gives you a velocity of almost 2 meters per second. But I'll modify that as we consider the roughness of the channel. So this is actually the inside of the elephant trunk. It's remarkably smooth. It has a roughness that's somewhat basically comparable to all sorts of basically arteries. This is the urethra, this is the artery, this is the windpipe. Basically all these biological tubes have really gotten as smooth as possible in order to reduce the friction and reduce the losses they get for the suction. So if you actually incorporate the roughness that you see within the wall, the Reynolds number of the flow is about 10 to the 5th. And with that, you can basically extrapolate basically what the velocity of the air is, given the pressure drop that we measured through the water. And with a friction factor, that gave us about 70 meters per second. So to put that in context, 70 meters per second is about 10 times faster than the human sneeze, and about half as fast as the AGV high-speed train in France. So it's really quite fast. I think it's remarkable to me that they can generate such high speeds with their nose. Now, what makes it's possible for them to suck are basically two things. One is that their lungs are quite large. They contain several liters. So basically, given this 72 meters per second, this high airspeed, they can actually suck for an entire 4 seconds. And you can imagine that's necessary while they're trying to figure out where the object is. If they were only to suck for half a second, it would be quite difficult. The other thing that makes this possible is the fact that they have wide nostrils. And this is the primary reason why other animals don't really use this mechanism to grab objects. So after I saw these elephant tortilla videos, I immediately went to my kitchen and saw if I could basically pick up a tortilla chip with my nose. And there's no way I could. But the best I can do is like with small pieces of paper. This is okay. This is a little bit like crack sniffing, which I've never done, but I'm pretty good with this paper. Oh wait, hold on. Okay. So if I could basically increase that flow speed to 70 meters per second, and I could hold it for about 4 seconds, I could basically grab food items. Now, the reason the elephant can basically grab such a large item is not because of its lung pressure. Because of the scaling of muscular forces in the area, lung pressure across animals from mosquitoes to elephants is basically around on the order of 10 kilopascals. And from our basic measurements of water, we found that the elephants have really the same lung pressure as we do. What makes it possible is just that the large diameter of their nostrils. The large diameter of their nostrils allows the airflow to sort of spread out, and that was given the equation I initially gave. Basically, it allows them to basically be, a substantial distance away from these food items to actually apply it. In our case, we measured that we theoretically showed is about, they have to be about 10 centimeters away. In practice, it seems to be about 4 centimeters. So they just have to figure out where the item is within 4 to 10 centimeters, and they just apply the magical suction, and it seems to work. And that height of 10 centimeters decreases as you go down with animal size. So basically, the largest animal underneath the elephant, this cow, would still need to be like within 1 or 2 centimeters. So it's unlikely other animals are using suction to pick up objects. And the elephants are also one of the few animals in which basically their manipulative apparatus, their hands, evolved with their ability to breathe. And so I think that was actually really important, that was not a coincidence that these happened together. With basically having such a long trunk and eyes that are very far away, if you basically could suck, then you could basically grab things. And maybe that's what resulted in the evolution of the trunk in basically the nose as opposed to some other part of the body. A lot of times elephants will, if they come to a watering hole, they'll be able to grab things underwater and be able to grab them. So this is also where vision's not very good. but they're able to use suction underwater. And they'll grab things and basically expel water out as they're sucking it in. We built this 3-armed robot. It's simply just with 3 actuators. But we wanted to see how useful sucking would be. So we basically gave it these very small pieces of paper on the desk, just like I demonstrated. And all we did was add basically just a suction device here. And without any extra control of the arms, you can basically get a 3 times increase in basically success rate just by having the suction there. And something they're actually starting to do in industry, there's a company in Schmalz called Schmalz in Germany that actually uses suction to grab boxes and other sort of flat items. It doesn't work with fragile items like the tortilla chip because of the preload that's required. So it's kind of a mystery how the elephant can actually, grab the tortilla chip and suck it without breaking it. So now I want to talk a little bit about how they grab smaller items. Here, you don't want to suck because the items can actually get into your nose. So here they basically turn their trunk into a broom, and the very last step, they'll create this kink in their trunk. And I'll show it again here. Basically sort of develop this sort of joint, and the position of that joint depends on basically how big the items are. The joint only appears at the very end of the grabbing maneuver. But here are sort of 3 images right at the end of the grabbing. And so the largest items, there's no joint at all. But as the items get smaller and smaller, what we see is that the height of the joint changes until it's almost 10 centimeters above the ground. And so when I saw this, I immediately thought of Benny Hockner's work. He's a neurologist in Israel who studied the octopus, and he showed that when you have an arm that has infinite degrees of freedom, it has problems figuring out where the food item is. So in order to sort of reduce the difficulty in making these choices, it actually forms a joint midway through. And it does that through basically as soon as it touches an item. This is why octopus don't have suckers all over their arms, because they don't just grab things at the tip, they grab things everywhere, and they can't really control where they're grabbing it, because it all really depends on where the food item is. But as soon as they touch an item, there's a neural signal that is propagated backward to the brain, and the brain sends another one forward, and where they meet in the middle, that's exactly the midpoint. And that basically forms one of the degrees of freedom to allow them to bend this thing towards the mouth. It seems to be the elephants that are also forming this sort of joint at a certain distance away from the food item. And if we look at we measure the force that's from this plate, we find that the force is proportional to the weight of the actual vertical part. So our hypothesis is that this slanted part of the trunk is sort of suspended above the air, and the vertical part is like hanging down. So it's basically using self-weight to compress these particles. The contact force that's necessary to basically compress the particles goes as an exponential function of the food size. And that's true for both elephants, and if you actually do this experiment at home, you blindfold yourself and try to grab items. If you were trying to sweep off items and pull them off, you do also apply a downward force to tuck them up. So it seems to be that that's actually really one of the best ways to grab these things. And the fundamental reason why it's an exponential function of food size depends on the fact that you need to basically form granular bridges. You need to form basically fixed arches within the continuum. So with smaller food items, you basically have a larger number of materials, and you basically have to prevent each of those individual materials from failing. With 1 or 2 food items, you basically just have to prevent 2 of them from failing. And this is Scott Franklin did the modeling for this work, but he showed that basically each item has a very small probability of failing. So when you basically consider basically piles of very, very large numbers of items, the probability of failing goes as 1 minus exponential of the individual probability. So the best this modeling can do is show that the exponent's negative. The rest is basically experiment. But this modeling shows that basically, as the food item gets smaller, the number of links that you have that you need to compress to prevent from failing needs to be very large, and basically you have this negative exponential. So that's why they need to do to grab things that are really small. Now let's look at the other end of things when things are really large. This took some time to train, but luckily the keepers are quite patient. But I'll give you an idea of basically what it took to get some of this data. This is actually the first time an elephant's ever seen a weightlifting apparatus. I think most people would feel the same way when they see this for the first time. What am I supposed to do with this? It's basically searching for food, just looking for food everywhere. And then this keeper is basically trying to communicate, hey, I just want you to lift this up just once, and I'll reward you with food. So here, just come a little closer to the bar. See this bar? It's supposed to go up. I was like, what am I supposed to do? I'm still looking for food. There's probably food up here. That's probably the best way to get food. No, I actually want you to wrap you around this bar, and we want you to lift it up. Pick it up. Okay, so that's when she realized, oh, this thing can lift up. And then from that, the rest was basically just doing the same thing over and over again. Okay, so this is weightlifting with 45 pounds. Really not that much of an issue for the elephant. It really does not look like 45 pounds, right? It looks like it's like 1 pound, but it's really quite heavy. Our videos, we haven't started to analyze how they wrap around the edge here, but it seems to be, they have a pretty firm grip on it, and they do it quite quickly. Okay, here's 65 pounds. And what I'm going to show in a bit is basically the shape of these trunks. And there's been measurements of the elastic modulus, and we can basically predict what the curvature should be to basically support this load without support the load that's provided mostly by the head motion. Yeah, so 65 pounds is really no problem. But I want my peanut. Okay. All right, now it's getting a little heavier. This apparatus actually looks like it's going to fall over. And we'll do the last one here, 135 pounds. And this line of chalk, so this is getting close to the limits. And so one thing we learned from this is that a lot of the strength of the elephant is really using the body weight. In this case, as they started getting to 135 pounds, I think you might just see in these videos, they really start to tilt their head back. But without basically applying their body weight, their trunk itself is not very strong. So these are the shapes of each of these different trials. And basically you can see the 45 pound is the least curved, whereas they basically get more and more curved. And this tells us that maybe the physical picture here is that the trunk is basically just an apparatus for allowing it to apply force to this region that's very far away. So because it's so far away, it's dealing with high torques. So the bar is a distance away. That's applying, and it has some mass, and so there's a force downward. So basically, it's got to basically apply a torque with this trunk. And it does so basically we consider this a beam with a constant elastic modulus. And so it basically has to figure out this radius of curvature so that, imagine if the elephant trunk was just a static beam, it should be able to support this. So we didn't actually consider any dynamics, we just wanted to consider what is the radius of curvature so that actually supports the weight. Now the key parameter here is this elasticity, the moment of inertia actually, so we assume that it's constant radius. The tip is the only part that actually starts tapering, but for most of the muscular effort, we consider that to be constant radius. It's between 10 and 14 centimeters in diameter. The elastic modulus has really only been measured once, and this was back in 1991, where Steve Wainwright and some colleagues they basically gave elephants some weights and asked them to do sort of unilateral compression of the trunk. And from that, they extrapolated that's about 1 million pascals. That's actually quite stiff if you compare it to the muscles of other living tissues. This is the logicus modulus of various animals. And the first thing I'll say, for animals, there's basically a range depending on where you measure. And from my perspective, that's not clear. For example, your forearm is about 10 times stiffer than your abdomen. And so there's maybe it's the density of the muscle fibers that allows it to be 10 times stiffer. The elephant is stiffer than all of them, according to Wainwright's measurements. It's all the way up here. So that's about 100 times stiffer than your abdomen muscles. And so that stiffness is applied basically in these muscles along the trunk. So this is actually an image from one of our dissections. This hole is actually there's not many of them, but there's these blood vessels that are actually supplying all the blood to this trunk basically to get the metabolism of these muscles. The radial muscles here, as I said, no one really knows what the purpose of them because they're like the muscles of our face. They're applied between muscle to muscle. So there's actually no bone in the entire trunk. It's applied from the sort of outer muscle down to this part. And we think that's involved in basically expanding the nostrils, but it's still yet to be tested. In general, the ventral part of the trunk is flat, and that's the part that curves. The top is rounded. And there's also sort of these muscles on the very outside, which they call longitudinal muscles. Those are basically going sort of from the proximal part to the distal part of the trunk. And there's also helical muscles that are not obvious here, but basically the radial muscles, the longitudinal muscles, and the helical muscles are what compose this, and what we think gives rise to the very high elastic modulus. So given this logicus modulus and the radius of curvatures that we measured, we were able to get a prediction that seems to be a pretty good match, suggesting that Steve Wainwright's measurement of this basically 1 million pascals seems to be probably pretty good for the stiffness of elephant trunks. 10 more minutes? Okay. So the last few minutes, I want to talk a little bit about these dissections. I was at UMass Amherst, and I ran into Benny Davidovich, and we were talking a little bit. I was saying the elephant trunks are quite wrinkled, and he was telling me about this scaling that had first been shown by Mahadevand in 2003, and has been used by various others. That basically, when you have a cylinder and you bend it, there's basically energy stored in two ways: one in bending energy, and the other one in stretching energy. And those are basically both in regions where basically there's high corrugations. For example, if you take a sausage and bend it, you'll get these corrugations, and when there's both bending and stretching of the tissue involved. And if the amplitudes are small enough, then you can show that there's one wavelength that basically minimizes the sum of the bending and the stretching energy. And that wavelength goes as the radius of here the trunk and the thickness of the skin to the 1/2 power. So is this actually true for the elephant trunk? We decided to actually measure some of the wavelengths and size of the ripples. So this is the elephant basically extending its trunk to its maximum extent. It's almost 50% longer than its original size. And here are some measurements of basically the geometry and the wrinkles. So this is measured basically from the proximal part. So the first thing I'm going to say is the trunk is tapered. We haven't used this in any of our previous modeling, but it plays a role in figuring out the wavelength of the ripples, because these wrinkles actually get sort of higher density as you go towards the tip. So, and this scaling is also not. We don't have a good explanation for why the scaling is basically almost to the -1 power. But the diameter basically goes inversely with the length, so it basically really looks like a cone. And that's also true in the living elephant too, except the living elephant, the entire thing has just been stretched. The skin is about 1% of the diameter. We haven't looked at other animals to see if that's the case, and these are basically different cross-sections of the trunk. This is basically all the way up here, then the middle part, then all you're getting to the tip. In all these cases, about 1% of the diameter. But because the diameter changes, it'll go between it'll go between almost 0.5 centimeters thick at the base to basically 0.2 centimeters thick. And for your reference, human skin is about 0.1 millimeters thick, about one sheet of paper. So an elephant's skin is basically like a book that's 50 sheets thick at its widest part. We physically measured the wavelength of these wrinkles basically from this dissected trunk, and we found that the wavelength matches, if we actually calculate the radius and the thickness, matches the correspondence that you get from those two variables. It works pretty well for the dead elephant trunk. For the live elephant trunk, it kind of there's an under-prediction, and that's mostly because most of the trunk does this extension near the base. So that's where basically the wrinkles actually start getting much wider than we can predict. The wrinkles are also strangely shaped. I haven't seen this before, but depending on where they are in the trunk, for example, on the base, they're sort of like a square wave. And then near the tip of the trunk, they sort of become more circular. So maybe this is a better way to sort of store strain energy, because basically they really don't want to. They're going to be stretching by almost a factor of 50%. So maybe this is a better way to store it, to have most of the stretching happen here. I think that we want to have 5 minutes questions. So I think with that, I'd like to see if you have any questions. Thanks a lot.
Questions for David. Please start. Can the elephant trunk with a needle or a blunt needle?
You mean like a spaghetti? A piece of spaghetti?
Or a needle, which is even smaller in length than its diameter.
I bet it probably could. I mean, the tip is actually covered with very, very stiff hairs that are almost like a broom. So basically, once it gets very close, because you saw that when it was actually picking up those grains of wheat, basically it hardly left any leftovers. So it's really kind of like a broom at the very end of its tip. So I bet it could. But we wouldn't feed it needles. We'd probably feed it something edible. Yeah.
I have a couple of questions. I'll start with the first one. The wrinkling, I'm not quite understand, because the theory is that wrinkles are created by compression, and that's why you have an instability on a foundation and you get these wrinkles. But then they should only appear on one side of the elephant trunk, because it's not obvious that both sides are compressed or anything. So what is the relation between that nice argument that we always see when people talk about, they put a picture of the wrinkling of the trunk, and the actual elastic instability and the actual trunk, right?
Yeah.
Is there any reason to think that it's relevant for that?
So let me answer that question first. So it's true most of those previous models considered basically something with no wrinkles initially, and then they bend this and you basically get these wrinkles. Whereas the elephant, there are permanent wrinkles. In fact, when the elephants are in embryos, they've shown there's wrinkles on the trunk. And you're right, they're actually on all sides. And they're not just sort of, we've only considered the wavelength in this direction, but because the trunk can twist and things, they're sort of in all different directions. Well, I think by having basically these permanent wrinkles, it basically, when it deforms, it always has the wrinkles in those same places. So I think partly it reinforces, but the other part, it prevents the skin from getting sort of damaged over the large
And also
numbers.
extensibility, right? Without stretching.
Yeah, and also maybe provides some sort of extra give when it's stretching. So I think you're right. It's just kind of a coincidence that seemed to match up, because we don't see any new wrinkles that appear. They're sort of basically the wrinkles that were there already.
Maybe it's like the wrinkles we have here.
Hmm?
Maybe it's like the wrinkles we have in this side of the finger.
Or
Yeah.
here.
Yeah.
Yeah.
That's excess skin.
Okay.
Have you analyzed at all changes in diameter of the trunk as it's used? Have you like put an elastic band around it with spots that you could measure the?
We have from video, and it appears that most of the change in diameter occurs at the top of the trunk, and that's partly because it's conical. I don't really have time to talk about it, but basically, if you're conical, most of the sort of extra extension you get occurs at the very top. So the very bottom has hardly any strain at all. So it's mostly from the base of the widest section.
I'm very curious about your suctioning. 6 liters relative to the size of this trunk, I'm guessing could be accomplished without using the lungs at all, but just by expanding the diameter, the overall diameter, and expanding the size of the cavity.
Yeah, because it's a tremendous amount of muscle that's surround. I mean, this is 100 kilograms of muscle, and a good amount is around it. So maybe that's sort of like an external lung, something they use to expand. We're trying to do some ultrasound experiments to measure basically if we can see some expansion.
Last question, Mimi?
Yeah.
So, two things. One is I wonder how important hydrostatic mechanisms are in making the trunk appear so stiff, and those transverse muscles could well be compressing all that blood and stiffening up, you know, to make the muscle appear so much stiffer than human muscle. And then the other thing, I couldn't hear what people were saying at the end about the wrinkles, but wrinkles is a wonderful way of not having to do any work to stretch your own skin. And if you look at our elbows, they're all wrinkly. So it's a way to be able to make a very deformable structure with a protective skin where you don't have to do any work on extending it. You're just doing the work on lifting peanuts and whatever. So those are just two
see.
thoughts that occurred to me.
Yeah. One thing we want to try to measure the diameter during the weightlifting, and maybe that will give some idea of how much blood has sort of gone into the muscle or how much it's contracted. But I think if you have extra blood, that you think that could increase basically make it more stiff.
Well, and also there are things called muscular hydrostats, and work by Bill Keir on squid tentacles is a really good model of that. So because muscle itself is incompressible, if you contract, for example, transverse muscles, you can stiffen the entire structure by a hydrostatic sort of mechanism.
Oh, I see. So you can stiffen it longitudinally if you contract transversely and stiffen the whole.
Or stiffen it entirely. You know,
Okay.
it's like blowing up a balloon to be stiffer. Yeah,
Yeah. I know the human tongue has a huge range in stiffness,
yeah.
like,
And so
like
it
over 100.
could be very much the same mechanism.
Okay, thanks. And thanks for the comments on the wrinkles.
Well, let's thank the speaker one more time.